All right, yeah, we can start now. I am a little bit unwell today, so I won't be maybe going through all the content. Uh, I'll try to go through most of it, and there's a session on Tuesday where I'll cover the rest if I have to stop in between. All right, is that fine?
Yes, sir.
What I have planned is the basic definitions of graph theory that I'll go through, and then some general problem descriptions of certain general problems, and then one particular problem that we will look at is topological sorting. There is also a representation of graphs that we will discuss. All right. So graph theory is in some way very independent of what we have been discussing until now. Until now, we have been talking about functions, calculus, continuity, differentiability. Now we come to the discrete setup where we are looking at least for this course, we'll be just looking at a finite set of vertices and relationships between them. We have seen it in some capacity earlier. When we talked about sets and relations, we did talk about finite sets and relations between them, right? So here we'll be taking a more graphical approach, and we'll see how many naturally occurring problems do take the form of graphs, and then we'll see how we will go about solving it, how we will give uh, algorithms to not necessarily uniquely, but just how to get a solution to certain things. This is what we will be looking at. And if you, this is a good time to even get back to the course if you want, because most of it will be independent of what we have done so far. So this you can start afresh, and if you can at least get these 2 weeks content covered, that does not require any backlog, right? So let's get started. And in everything in graph theory, it's always good to keep a picture in mind and work through with the picture rather than just uh, look at the mathematical definition and say, okay, if there is an edge between these two vertices, then you should always think about it as you can have once I give you a few prototype examples of graphs, you can keep one of them as uh, a prototype in your mind, and whenever we discuss any concept, you can see how what interesting questions you can ask for the types of graph that you have in mind. So actively you should try to connect it with real world problems rather than just learning it as a subject of mathematics, theoretically just learning it. All right, so let's get started with what is a graph. So every time I take up any topic, I will give you a mathematical definition and, of course, an interpretation of how to think about it. So, first, the mathematical definition. A graph, usually denoted with capital letter G, consists of two things. One is called the vertex set V, and the other thing is called the edge set E. Is a tuple where V is a, well, we can just call it a set. Here we'll be assuming a finite set, and E is a subset of V cross V. Where have we seen subsets of V cross V earlier? Any?
Cardinality.
Not for cardinality. what is a subset of A cross B? It's a relation, right? So if you have a relation on a set, suppose you start out with a set V and you're talking about relations on that set, you just consider subsets of V cross V, right? Now, as it is, this just looks like just a set, and then you're taking a choice of a subset. So why is it called a graph? So let's take an example and gradually shift to the understanding of this definition rather than just reading it out loud and understanding the terms there. So suppose my vertex set is 0, 1, 2, 3, and I take the following edge set. So everything over here would be a, a tuple. So let me just take something like this. I'll take a symmetric relation in the sense that whenever there is 0, 1, I will also put 1, 0. This is just for this example. We'll see what it means.
It means 16 subset.
Not necessarily all the elements. I'll just take some of them.
Okay.
Let's just stop over here, maybe. Okay, I'm just taking. Yeah, go ahead.
Sir, it depends, the number of elements we take, it depends on the given question, right?
Yeah.
How
So
it
this
is
is a
taken.
particular example.
Okay.
Sir, and
Okay.
Sir, what is the meaning of tuple in this?
A tuple is just a set of two objects. It's just there's this vertex set and this edge set together. We call it a graph.
Focus. Thanks.
Right. All right. So now what you have to visualize is that you look at these. Since we called them the vertex set, let's write them as vertices. And then 0, 1 and 1, 0 are there. So I'll just join that. Right. 1, 3 is there. I'll join that. And then you have 1, 0 is there, 2, 3 is there, and 0, 3 is there. So this is, of course, how you should see graphs.
Sir, but cannot we direct it if
When we direct it, we don't need to have the symmetry property. First, to keep it simple, I'm just doing undirected graphs. So here I'm just saying, so when I say it is E is just a subset of V cross V, this would be a directed graph where you are not imposing the condition that if A comma B is there, B comma A is also there. So let me write that.
Yeah, symmetry will be, yeah. Okay.
So a directed graph is this. So, and here I'll just put arrows. So the graphical, when I'm talking about the graphical representation, if 0, 1 is in the edge set, I will say that there is I will just denote it by 0 to 1, the arrow going from 0 to 1. But in this case, by construction, what happens is everything is bidirected. So I'll just remove that and I'll call this an undirected graph.
So if it is in one direction, then it is a function? Means all.
What is a function? Not necessary, right? So why would so you can have some graph like this. You can just have this as a graph. So this will not go to anywhere. So that so there is no relation between functions between from V to V and so on.
Okay.
Okay. So this, just think of it as formally writing down relationship between elements. So for example, you want to list down the huge network of people and whether they are friends on a particular social media platform. So following someone on Instagram, let's say, the vertices will be all the people in the world, right? Or all the people in the world that have Instagram accounts. This will be a huge vertex set, finite, but still very huge. And this will be a directed graph, right? someone might follow someone, but the other person might not follow them back. So
Yes.
this is a very classical example of a graph. If you don't want such a huge vertex set, you can even just plot it in a classroom and say, let's say there are like 6 students in a classroom, and there would be an edge between 2 students if they are friends with each other. For now, let us assume that friendship is both ways. If they are friends with each other, if both of them consider the other person a friend, we will draw it. So in this case, you don't need a directed graph, right? You if I'm a friend with the other guy, the other guy is a friend of mine. So that this would be a two-way relationship. There might be some vertices, there might be some vertices missing. Now let's say this is my graph, right? So just by looking at it, it's a very good
Excuse
visual
me, sir.
representation. Yes.
What do you mean by some vertices missing?
Some vertices missing?
Yeah, just you have told.
No. So there might be some vertices isolated, as in I might have not said it correctly. There might be some vertices isolated. That is also okay.
Okay. Means they have
Okay,
no
so
friends with anyone.
yeah, they are solitary people.
It means these are not
Okay.
affected by them.
So they have no edge connected
So
with
they have no
them.
edge, right? So just by if I tell you that this is the representation of the ecosystem of the classroom, you will know who is the most social person or who is the most solitary person. So graphs do contain a lot of information.
Yes.
And right. So, but if I were to write this just mathematically, I would write G is equal to name 1, name 2, name 3, name 4, whatever the number of names, and edge set is this comma this comma this, and so on. So this representation of vertex set and edge set as a subset of V cross V is important, but the picture is worth 1,000 words, they say, right? So similarly, graphs do represent very important relations between vertices. So whatever the vertices may be, this is a very, very simple example of what vertices are, right? Another very classical example of vertices would be, so let me write this down for people who look at it later on. Friendship graph in a classroom. So it could be something like this. This is one example, right? That I'm just keeping it simple and saying it's a undirected graph, meaning friendship always goes both ways is what I'm assuming. That could not be the case also. But if you want to have a more objective evaluation of who's following whom, for example, you could even just track the Instagram accounts of the people in a classroom and draw arrows from one person to another if that person is following the other person. So that is also one example. So that would be a directed graph, of course. Following may not be bidirectional. Another thing is if you can just plot the course structure for your BS data program, you have something like Math 1, Stat 1, CT, what is the other thing? English 1, right? English 1, and then English 1 leads to English 2, Math 1 leads to Math 2. But for Stats 2, I think you need both Math 1 as well as Stats 1, right?
Yes, sir.
And for Python, you need only CT, I believe.
Yes.
So is Math 2, does Math 2 only require Math 1?
Yes.
And but Stats 2 requires both Math 1 and Stats 1, right?
Yes, sir.
And English 1 and English 2 are like independent of each other. And CT and Python are also like that, right?
Sir, I have a question.
Yeah.
In the above graph,
the friendship graph. If
Yeah,
we say mid vertex, the one in the middle, and
this
the
one. Yeah,
ending one on the right corner.
this one.
Yeah, yeah,
Okay,
the connected ones. No, the mid one on the right.
this one.
Yes.
Okay,
So can we say that these two are also friends of each other? Because the
they're not
line is
friends
not
of each
correct.
other, but there's not an edge between them, but there's a path between them. So you can reach one person,
Mhm.
you can reach from this person to the other person through a network of friends. This does become important later when we talk about reachability and so on.
Okay.
So, so let's say, yeah, we will actually talk about this later. But let's say this person needs help with something which he or she is they are not qualified for. They need some external help. Now, first of all, they'll ask their friend, but in this case, they only have one friend. That friend might not be able to do that job. So they'll ask their friends if they can. So suppose this is the only person that can help, and but this person can reach this person using this network of friends. So there is a path between these two vertices. So reachability is a very, very important problem in graph theory, where we ask whether a particular vertex is reachable from whether every vertex is
Sir,
connected to every vertex. That is the broadest or class of problems. But if you want particular one, you just pick one vertex and say, from this vertex, can I connect to everything? In this graph, obviously, you know that not all vertices are reachable, right? What are the vertices which are not reachable?
The
that
corner
2 points.
ones.
Yeah, the isolated ones, they are not
Okay.
reachable. So for an undirected graph, for a graph where there is no direction for the relation, of course, you can just look at it and say which are the connected components. Now, let's say there is another circle, even if let's say there is this sort of there are these three students which are like, okay, they are just not exactly solitary people, but uh, they have their own thing and they are disconnected from this other part. Even then, any vertex in this set of three, let's say this is the part 2 and this is part 1 of the graph.
Yeah,
Sir,
then
Yeah,
three dots are also isolated because of them. Yeah.
there you could call those three are isolated, or you could call these whatever 1 2 3 4 5 6 are isolated. So
No,
it's they are just two different components, so they are not isolated as such. An isolated vertex technically would imply that that is not connected to anything else.
yeah.
Okay.
sir, but the
Okay, so
reachability must be according to the situation. Now,
yeah, so in this case I'm
supposedly,
just
if there
yeah,
are
go
two
ahead.
vertices, if we follow the path, and if the
Hmm.
path is followed, given that the path is followed, then the both people are connected to each other.
Yeah, so
Direct.
for example, this person and this person are not connected, right?
If
So that can
there is
happen.
path, if there is a path, and if
Hmm.
we follow the path, if it is not direct,
If
but
it is not
when we
directed,
but yes, if yes, there is no direct path.
right?
It's not about a
And
path, this is just a relation.
if we follow that and we reach a point where,
So what's the question?
sir, my question is, suppose the two crosses you made here, the
So
paths,
these vertices, is it? Let's
yes,
give them names,
yes,
no? Let's give them
yes.
0, 1, 2, 3, 4, 5, 6, 7, 8.
Okay, now 4, 5 are not connected, right?
Yes,
To reach 5, if 4 needs a help and only 5 can do the help, 4 contacts
yes,
1, 1 contacts
yeah,
2, 2 contacts
yes,
5.
yes,
Ultimately, we are connecting 4 and 5, right? After the
yes,
contact happened, we are connecting 4 and 5 because now 4 and 5 are in contact, direct contact.
Well,
Asking
you
four
could say
more.
that five helps four, but they need not be friends. It can be a transaction also, right? So,
Okay, now I got it.
all that is there the human element does come
Yeah. If
in.
4
Uh,
follows
uh,
5, then 5 also follows 4. Yeah, ultimately.
It is not the thing, but they come in contact. If they are not in contact, this
Yeah,
is
yeah.
yeah, coming in contact is not necessarily friendship, right? So
yes,
let's just assume that and move ahead. Is that okay?
yes, sir.
Yes, sir.
Yeah. Now this is also a graph. So this is your let's say clearing of foundation level, right? So to clear foundation, you do need all four, right? So this is also a graph, and there will be something called topological sorting that you will see later. In this case, the sorting is very simple because there are very few dependencies. In this case, actually, let's not do this foundation thing. Let's just list out the foundation courses and then just let's draw arrows. In this case, we have to draw arrows, right? M1 is required for M2, but M2 is not required for M1. So that is not how it works. So this is a very simple graph of dependencies between courses. Now, instead of courses, you can also take a set of tasks that need to be completed. Let's say while building a house or while scheduling any sort of sequence of events in which some things may be dependent on some things. So there you have to draw arrows from the thing that needs to be finished first to the thing that needs to be finished, that can be done only after that other thing is finished. So that is also one very uh, classical example of a directed graph. Task dependency is what I'll just call this. Is this clear why this is a directed graph?
Yes, sir.
And another one which Professor Madhavan also uses a lot in the videos is connectivity between cities. Or now I'll just draw 4 cities. Now, let's say there is a direct flight from here to here, and there is one back. And for whatever reason, there is a direct flight from here to here, but not anything back. So here there is just a flight from this to this. In this case, reachability becomes so reachability in an undirected graph just means whether you can find a path. But here, when we talk about reachability in a directed graph, you also want to follow the direction of the graph. Let's say you have something like this. Is every vertex reachable from every other vertex in this case? If is every city reachable from every city? I don't want direct flights necessarily. I can take layovers and
Yes, sir.
take connecting flights.
Yeah, it will be connected.
Can you go from any city to any city?
No,
Yes, sir.
we cannot
Yeah,
go
yeah, yes,
from
sir,
two
yes.
to any other.
No, we can go.
What about two? Can you start from two and go anywhere?
No, no, no.
No.
2 is not, yeah.
Two is not,
Yeah,
right?
yeah.
So let us talk about just reachability of a single vertex. Starting from 0, can I reach every other place?
Yeah, it can be reached from 1 and it can reach from 3 also. And it can reach from 2 also, yeah.
So from 0, you can go to 1 or 2 directly using a single edge, a direct flight. But there is no direct flight between 0 and 3. But that's
Yeah.
okay. I can take a flight to 1 and
But
then
we
go
can
to 3.
reachable, yeah. But we can reachable, yeah.
Yeah, it is reachable. So this is not a good planning of flights because if you are a person in 2, you do have no choice. This your airport is basically useless. So you would want you can measure reachability if you have algorithms to see how to close this or how to make everything reachable. That is another graph theory problem. Now a very real world problem translated to graph theory. So in most of the rest of the session also we'll be looking at statements of certain problems, and the actual algorithm. So we will talk about one particular algorithm which targets this task dependency problem, but the reachability thing, I'll take it up on Tuesday. All right. So at least now, have you an idea of what a graph is mathematically? It is just a finite set and a subset of V cross V. For a directed graph, we would say is anything, but for an undirected graph, we will just say that it's a symmetric relation. For a directed graph, it is any relation. Also, there are some points here that need to be noted. This is not just any subset of V cross V. Vertices of the form A comma A never belong to this. Okay, A comma A does not belong to E for all A. So this is like the opposite of a reflexive relation. Why? Because what would that mean in the context of a graph? There is a self
Undirected.
loop, right? So there is an edge from a vertex to itself. These are also there in graph theory, but in the context of this course, we are not going to deal with graphs of that manner. So in our graphs, there are no self loops. All right. So there are certain conditions, but you should be able to freely go back and forth between a diagram and the data just presented this way. Okay.
Yes, sir.
Right. So types of graphs, directed and undirected, we have seen. Let me just write it down. If the edge set is a symmetric relation, then the graph is undirected, right? So there, otherwise it is a directed graph, right? We also talked about paths in a graph, reachability. We talked about what is reachability. Let me just state it properly. A vertex. Yeah.
Can we say that if a graph having a direction, then we can say that the graph is directed if the direction
So
is
in the
not
questions
there?
that you'll be asked, you will be given the graph diagram most of the time directly. So there, if it has, see, an undirected graph also can be thought of as a directed graph with two-way arrows everywhere. So the directed graph is the more general way, but instead of writing those arrows everywhere, both-sided arrows everywhere, we just get rid of it and call it an undirected graph.
Yeah, we ignore it.
Yeah.
So can it be drawn by two directions, means two arrows if we draw in a edge, between an edge? So
Yeah, that's
can
also fine. So, but the nature of the problems, you will have the graph representing some phenomenon where whether it is directed or not will be obvious to you. Like, let's say you're taking a set of people or set of houses in a neighborhood, and then ask if and the houses are the vertices, and then you have the neighborhood, as in, are they neighbors of each other? This is the edge. Is this directed or undirected?
neighbors are
Undirected.
edge?
So a house one is, there is an edge between house one and house two if
Yeah,
they are next to each other, if they are direct neighbors of each other.
undirected.
This is undirected, right? Like, so there's no way, like, okay, this guy is a neighbor of mine, that guy is, of course, then this will also, the other guy will be a neighbor of this guy. There is no
Yeah.
way that it can be a one-sided relation. On the other hand, if I have, let's say, a set of people in a household, and I say the relationship is person 1 is connected to person 2 if person 1 is a parent of person 2. Is this a
So
directed
this
or an
will be
undirected
a
graph?
directed graph.
This will be a directed graph, like, so it can't go both ways. Even prerequisites, for example, that for the task dependency thing, if we have one task to be a prerequisite of another, this is of course going to be a directed graph. Now, there is one more class of graphs which we will see later. They are called weighted graphs. So we are not looking at weighted graphs for now, where we also, I just mention it now since we have already discussed a fair set of examples. So take, for example, flights between cities. This example of flights between cities. Right? In this case, let me also add one more edge over here between 1 and 2. Here, the information that this graph just gives is what cities are connected to what cities through flights. But it doesn't talk about the cost, right? So if I assign a cost to each edge, right? So the cost of the cheapest flight, for example, if I write that down over here, I can ask even better questions, right? Like now that I know 0 and 2, the cities 0 and 2 are connected. How will what should I do how should I go from 0 to 2? What is the answer?
It will be directed
By
0 to 2.
Directed or
by
via 1.
It is directed or via 1. So what is
No,
the
it will be
choice?
direct right from 0 to 2.
But you know that even from real world that sometimes the direct flights are more expensive than taking one with a layover, right?
yes.
So
Yeah.
there, the cost of this edge also would matter. So if your objective is not just to look for connectivity, it is also to minimize the cost. So many processes, not just flights between cities, can be represented in graphs where each edge is a process, and that process has some cost. And the question is not whether I can go from this vertex or not. That is a preliminary question where if I cannot, then done. So reachability is the first check. But after you do reachability, you also would want to know what is the shortest path. And
So
to do
basically,
that,
to gain something, we have to lose something. Yeah.
not you don't need to lose anything, but maybe the 0 to 2 is also the cheapest path also. That also can happen. The connecting
Yeah.
flight may be expensive, may not be, but without the knowledge of what the edge cost is, you cannot ask such questions. So that is where weighted graphs come, where in addition to a vertex set and an edge set, there is a function called the weight function from the edge set to real numbers. Each edge is associated a real number, which we call the weight or the cost. So if you take a path from 0 to 1, then 1 to 2, the cost of that path would be weight of the edge 0, 1 plus weight of the edge 1, 2. Whereas the direct edge from 0 to 2, that will just have the cost of the weight of 0, 2, right? Now you have to compare. For a small graph, you can just maybe look at it, but considering the number of cities, the number of connections between cities, if you talk about it globally, you can see how congested this is and how not doable by just looking at it is. That's why we design algorithms and we have systems that are fed the algorithm, and you can just maybe put the names of the two cities and you will get the best way to get from one to another, right? This is what many applications offer also. It will calculate the cheapest way to go from one place to another. There are applications that offer this service, right? So they do this in some way. All right. So where were we? Directed and undirected graphs we have seen. Weighted graphs I've just mentioned. I've not written it down right now. Whenever it is required, we'll introduce that. Now paths. Now we have already talked about paths. Let's formally define it now. A path in a directed graph. I'll talk about a directed graph. You can talk about undirected graph also. From, let's say, vertex U to vertex V is a sequence of edges of the form U comma, let's say, W1, W1 comma W2, and so on up to Wn comma V. This is just whatever we have written down, right? Like whatever we had talked about earlier. What is the path from this friend 4, the person 4 to person 5? We went from 4 to 1, 1 to 2 in the friendship graph I'm talking about now. 4 to 1, 1 to 2, 2 to 5. If you're talking about flights between cities, 0 to 1, 1 to 2, this is a path between the cities 0 and 2. So in general, you can have as many finitely many vertices as you want in between, as long as you start with U and end with V. That is going to be called a path from vertex U to vertex V. Now the reachability question is the following. So these are a few questions related to reachability. We have discussed these in some capacity already. So the first question is reachability between a pair of points, right? Given vertex U and vertex V, is there a path from U to V? So this is we are just stating the questions. We are not answering them just yet. So that is the first question about reachability between vertex U and vertex V. This is for very two specific points. And then we also talked about shortest path between vertices. This does require the notion of weight of the edges. So just because we established that V is reachable from U, that does not mean the path is unique, right? So there might be multiple paths, and which is the one with the shortest cost or least cost. So among all paths from U to V, which is the one with minimum cost, right? This is a reasonable question. So whenever we talk about anything, right, any question, anything in graph theory, when we ask, so think of it as not abstract, vertices U comma V, then from the edge set I need to find a sequence U W1 W1 W2. Don't think of it that way. Think of it with the picture, a picture of whichever model of graphs is favorite of yours. You can take that as a model and think. So for this one, for the reachability thing, the connections, flight connections between cities is a very good model, right? So this is a very reasonable question. Is there a path from U to V? Ideally, there should be a path between every city to every city, every place to every place, and there is not necessarily by flight, but if you include more modes of transport, you will get that, and then there will always be multiple paths. Whenever we plan a journey somewhere, we do take that into account, right? How much cost? Now, cost may not just be money. You might go for a more expensive option if it is a very quicker one. If you can, if spending that much is not too concerning for you. So the cost, even though it might sound like associated with money, it need not be that. It might be the time cost
So,
also.
sir,
Yeah.
sir, if two paths have same cost,
Then both are okay. Like both are, and they are the minimum. If there are two paths, which whatever version of cost that you have, according to that cost, if there are two paths, then you can take either of them,
Sir,
right?
I have a question.
okay.
Yeah.
Sir, suppose I am collecting a data and
Mhm.
I'm just binning my data. And according to that, I made nodes and edges like that. And after
Okay.
finding ways, I mean, I just bin my data. First, I have to do data collection, but after analyzing, I found that there are n number of nodes from suppose say n minus 1 nodes, n minus 2 nodes, which can be clubbed in. Means I can reduce that. I don't need that after finding the intersection. So
You may have to
what if we
be
can do
more
with this
specific
also?
about what you're going for.
I
What
want
do
to
you mean
reduce.
by clubbing together?
Yes.
So do you want to take up a particular example and say where clubbing together can be possible?
Suppose I took a data for getting good marks.
Shall
Somebody
we go to the common graph problems, because taking a specific subset of vertices which makes sense or which achieve a certain purpose is a common theme for the problems we will discuss below. Maybe after we discuss that, your question will make even more sense.
Okay, sir.
Shall
Yeah,
we
I
do
have a
that? Shall
question.
we
Yes,
just go
sir. Of
ahead
course.
with the
As you
yeah.
like.
Yeah. Yeah, there was a
Can I
question.
ask a
What was the
question?
question?
Yeah.
Yeah,
You
sure,
wrote
go
that
ahead.
you wrote, is there a path from V U to V? So the path need not be direct, right? It can be indirect. I mean, by indirect, I mean
Yes,
when
a path is
we
a
talked about
sequence.
the friendship graph. No, no, listen to it. Listen.
Yeah,
When
so when
we
I say
talked
a
about the
path, okay.
friendship graph, it was connected from 4 to 5, right? So the path can be connected from U
Mhm.
to V in such a way, right? That is okay.
Yes, that's okay. So here, see, the path is defined over here, right? It's a sequence of edges. So in that case, see a path from 4 to 5. This would be 4, 1, 1, 2, 2, 5. This is path. A
Or
path need
prices
not
may
be an
be
edge. A path is a combination of edges.
Yes.
okay, sir. Suppose if a flight U and
All right.
another flight V, if the U flights goes towards
Mhm.
V with the price of 100 rupees, and
Mm.
V flight goes towards U, will be price change or same? It may be happen.
That depends on the real life data. So we are just saying this is how we can model it. What happens in real life, you will have to make changes to your graph accordingly.
Yeah, I am asking that it may be change. Okay, yeah.
Yeah.
Okay.
That could be the case, right?
Okay.
And well, in real life, you won't even have a fixed cost for a flight. It is a dynamically changing thing. So today it might be something, a few hours later, even it might be different. All those
Okay.
things we are not going to worry about. The extent of real world applications is we'll just say that these are all the cases where you can see that graphs are the right model to work with.
Okay.
So these are cross-section series, right?
Sorry.
No, I mean this is cross-section data. The graph
What is cross-section data?
means means we collect that for at that time. Suppose stocks.
Yeah. Okay, that you can think of it that way. At a particular point of time, if you want to just snapshot the data and then want to represent it in terms of a graph, you can do that. That is a valid way to look at it. All right. So
I
bear
think
with me.
what he is asking is all the graphs are cross-sectional data?
Graphs, the weight function can be a function of time, and then you can introduce one more parameter and so on. But let's not go there now.
Yes,
Like,
sir.
I don't think you will be even doing it in the entire course, because here we are just looking at static things. Ultimately you're dealing with graph theory, the mathematical subject. But I'm saying all of this because this is one area of mathematics that is very, very easily translated to real world things. So this is how you should think about it, is what I believe. So that's why I just pointed out where, like, very common normal things where graphs are the right tools to look at and ask questions. All right. So the third thing is, okay, here in the first question, we started out with a particular pair of two vertices, u and v. And then we said, is there a path from u to v? But in the third question, we'll ask something more general. If I start from a particular vertex, let's call it v, can I reach every other vertex? Well, this might not be the question.
It depends on the graph.
Yeah, so, or can I determine the set of all vertices I can reach from there? What does reach from there mean? I need a path which starts at vertex v and ends at whatever vertex of interest. In this example, in this undirected graph example, you can clearly see there are like two components. Each of them are connected. So if I pick a vertex from here, if I pick a vertex from here, you cannot reach them, right? You cannot. If I start with, let's say, vertex 3, there is no way for me to go to 6, 7, or 8. And you can always reach any vertex from 0, 1, 2, 4, 5. But in a directed graph, it is more interesting.
Sir, it is possible.
Possible. What is possible?
No. I considered if I consider it in 2D plane, then it is not possible. But
Well,
if I
we are
plot a
not.
point in 3D plane, then I might
See,
get.
we are not talking about 2D or 3D. Here, the data mathematically is just a set of edges, right? The edge set is given to you. Can you construct a sequence 3, v1, v1 comma v2 and so on, which ends in vn comma 6 or vn comma 7 or vn comma 8. That is not possible, right?
Yes.
So this is yet another thing. You should be comfortable talking in terms of vertex set and edge set just abstractly in terms of the labels that are given, or you should be and write the corresponding diagram for it and visualize it. Or if the graph diagram is given, you should be able to convert it back to the abstract data. What is the vertex set? What is the edge set? What is the mathematical question being asked? If you have a fluency between translating from abstraction to visual things, then that will be a very good tool to have, right? So when we ask, is there a path between or is R3 and 6 friends? Instead of thinking of it as two-dimensional, three-dimensional thing, just boil it down to the basics. You're asking, is there a path between 3 and 6? What is a path? A path is a sequence of edges which starts from 3, ends at 6. Is there a sequence? We clearly see that there is not. To prove it, it will be it's a different thing. But at least when you see it, you can see it, right? Like if I do 3, 0, then I can go to 0, 1, maybe 1, 2, 1, 5, 2, 5, 1, 4, all these things. But there is no way I can jump to 6 within the finite set of edges that is given to me. Okay, so connectedness. So we are in question 3 right now, where if I start with a vertex V, can I determine the set of all vertices that I can reach from there, right? So now, even while talking about flights between cities, this example of flights between cities, we saw that vertex, if I start from vertex 2, what is the set of vertices that I can reach?
No vertex.
No way, sir.
It's an empty set, right?
Yeah.
So it just, practically that would not make sense. Like if the flights come, they have to go somewhere. So don't think about that for now. That is an empty set. But we said that for 0, what is the set of vertices that are reachable?
1 and 2.
Not 3?
Yes.
Yeah,
And
3
3.
also.
One, two,
And
1,
3
2,
also.
3.
1, 3.
So for 3, you can go from 0 to 1 and then 1 to 3.
Oh,
So
okay. Yeah.
it is reachable. So
Yeah.
Yes, reachable.
from 1, what are the reachable vertices?
Yeah, it may be 2 and 0, and it will be 3.
0 to 3.
0, 2, 3,
sir,
and
but
all these are collected by a
reachable.
single edge even.
Yes. It is 2 and
Right.
1.
From 1 to 2 and 1
How
to
1,
0, and
right.
then and again I think from 0 to 3 we can go. So I think 0, 2, and 3.
Yes.
So for 1, everything is reachable. From 1, everything is reachable. From 0, everything is reachable. From 3, is everything reachable?
Yes.
Yeah,
Yes, sir.
yeah,
Yes, sir. Yes, sir.
Yes.
yeah,
sir.
yeah.
Yeah, right. So in this case, reachability starting from each vertex, we can visually just look at and determine, but we will need an algorithm to do it systematically, which we will see. Perhaps not in this session. Yeah.
The flight graph which I've given now, will we call it like unidirectional graph or like directed graph?
It's a directed graph. It's a directed graph. Not all, there is no, for example, look at vertex 2. If this was an undirected graph, 2 and 0 are connected. So there's no information of start from and going to. If it's an undirected graph, it is just connection between two places. So the same thing, if you assume this graph, and if the edges were not, does there exist a flight from this place to this place? And instead assume that the edges denote whether there is a road from this city to this city, direct road from this city to this city. So in that case, it would be an undirected graph, right? The existence of a road will not be like there is a road from 0 to 2, but there is no road from 2 to 0 will not happen. But
Yes.
in the case of flight, this can happen, right? So even that is very unlikely, but just for the sake of argument, we have taken that just for the sake of demonstration, we have taken that there is a possibility that a flight service runs only from one in one direction. So that direction is important. So
Oh.
this vertex in particular is a two-way thing, but everything else, just for demonstration, even though it might not be realistic, I've said that in all of these cases, there's just a
Sir,
one-way
I have a doubt.
transport system. Yeah.
So basically, even if there is one path which is undirected, no, I mean directed, and there is, as you said, 0 to 1 and 1 to 0 is happening, but the other
Mhm.
ones are directed, more or less. So then it becomes a directed graph.
Yeah, it's a directed graph. Yes. So if
Even
the
if there's a
direction is
presence
given,
of, yeah.
yeah, that's fine. In
Okay.
fact, most directed graphs will share that feature that some of the graphs will be, some of the edges will be bidirectional,
Hmm, hmm, hmm. Correct.
and some of them won't be. In a realistic flights between cities, I would assume most edges will be bidirectional.
Right.
Because if
Because
the
I think if it cannot be possible that if there are vertices, if there are three vertices, it
Mhm.
cannot be completely undirected. No, sorry, directed. No, undirected. Yeah. Um,
I didn't get your point. What was the last doubt that you had?
yeah, as in, it cannot be undirected if there are just three vertices, right? And if there is a path from, let's say, like 0, 1, 2.
No, if you have three vertices, it could be directed or undirected. I can have something like this, or I could have something like this, or I could have just a graph which shows connections between two couple of things, whatever you're
So
interested in.
the second one is
So you
undirected.
can consider means an airport
The second,
where the flight has been delayed.
um,
For as we are seeing for time.
Just one moment. Let me address the other
yes,
person's doubt.
thank you.
What about the second graph?
Yeah, the first one I got it. The first one is just one way, right? So it is a directed graph.
Yeah,
The second one is
also a directed graph, because here, even though everything is connected to everything, there is no direct edge between in both ways
right.
for every connection, right?
Yes, sir. So that is what I was saying, that it cannot be undirected if there are 3 points involved, right? In a way.
So this last thing is undirected graph. You could have
Okay,
it in such a way that,
got it. I can
yeah.
go
So
from A to
whether
B,
you
B can
give
go to A. Right,
a direction or not is up to you. It's a choice.
right. So yes, got it. Thank you.
Sir, so for being undirected, every vertex or every edge should be like two-way in the given graph.
That's one way to look at it, but you could just think of it in terms of the relation that we are just given the order of the way in which the vertices appear in the edges doesn't matter. Uh, it's just a two-element set of a subset of V. That is also one way to think about it. So in pictures, if there are no arrows drawn, it's an undirected graph. If there are arrows drawn, it's a directed graph. Right. So this is a simple way of looking at it. And if you want the interpretation of the graph, then an undirected graph would be an interpretation of a phenomenon which is in some way symmetric. So
yes, sir. So
by design.
can we say that if all the elements are symmetric, all the pairs are symmetric in the given
Yeah,
set,
if the relation itself is symmetric, if E is
then it
equal
is
to V cross
undirected.
V, yeah. So you have just restated what I've written over here.
Yes. So if it is A, B, B, A, and C, yeah, like it goes on and on. But if there's one element which is not symmetric, if there is just like, let's say X, Y, but no Y, X, then the entire graph becomes directed for that matter.
A directed graph, yeah, a directed graph with all but that vertex.
Right. So that one specific, yeah. So that one specific
Yeah.
case makes the entire
Yeah,
thing directed, right?
Yes.
Okay, got it.
Sir,
Thank you so much.
So for this, are we following that symmetric relation or transitive relation?
It's
In
just
the
symmetry.
mathematics, yes, symmetric relation, because if there is 1, 2, 3, then set is 1, 2, 3, then there must be 1,
Yeah.
comma 1, 2,
Yeah.
comma.
So when you talk about transitivity, what is it? It is if there is this, if there is this, there should be this also.
Okay, I got
So
it.
that is not what
Sir,
we are talking about. We do talk about reflexivity a little bit because we don't want self loops. So we say it is as far from being reflexive as possible. And symmetry or non asymmetry of E is for directed or undirected.
sir,
Yeah.
sir, for transitivity, the example would be friendship graph, right? Means, for getting a friendship from, uh, let's say, if you say from 2 to 5 and then 5 to 6, then it represents transitivity.
No, so let's say here 1 to 2 and 2 to 5.
Yeah.
1 2 is there in the edge is in the edge set in the relation. 2 5 is in the edge set, but 1 5 is not, right? So I can be friend with some person, and that person could be a friend with some other guy who I'm not friends with. It's not a transitive relation.
So, sir, if I connect 1 and 5 to an edge,
If you
so
connect
in
and
that
1 and 5, so
time,
what you're talking about is called the transitive closure. Like what
Will form
edges
a
you need to add
cycle.
to make it a transitive relation. Okay, that also is there in weak 11 content. Transitive closure of a graph.
That it will form cyclic, yeah.
Okay.
so transitive relation would not be considered in this case.
No. We are not. See, we are just
Got it, sir.
talking about the properties of symmetry, reflexivity over here. We are connecting it with the things, the terminology that we already know, and
Yeah.
it does make sense, symmetry and reflexivity, to interpret the properties of E in terms of that. We saw that self loops are not there because of this condition, and that is something like opposite of reflexivity. And symmetry, we will ask for if the graph is undirected, and directed means it will usually not be symmetric.
So, but
Okay.
let's say if one of the elements is not is directed, so in that case, except that element, I can say the graph is undirected.
No, you don't
Can,
say. I mean, you could say that, but that would be a confusing terminology. So that's why, if even there is one thing which is only one directional, it is better to write arrows, two-sided arrows for everything except that thing.
Okay. Focus.
If you just put arrow on one and leave everything empty, other than that empty, with the understanding that,
confusion will arise.
yeah. So just put arrows. Arrows are adding more arrows will just make it clearer, right?
Okay,
Wherever
sir.
there are bidirectional arrows, let them be. Wherever there are only one directional arrows, let them be.
Sir, I talked about 3D because in one of the practice assignment we are given resistor questions where there is a cubic
All
array
right.
of resistors. So
Mm-hmm.
can you just explain how to do that question? I got that question, but what if there is another question of that type? So
The graph could be in 3D, but the data is still in terms of edges, right? What edge set you have. The edge set is just a set of coordinates, like tuples. Tuples meaning A comma B, coordinates of the form A comma B. Even if it is a cubical resistor graph, even if it is a graph, something like let me draw a better thing. So let's say this is in 3D and you have something like this. Even if it is not the complete cube, it is still a set of vertices, and to write what edges are connected to what.
edges are
Right?
connected to the nodes. I mean, sorry, vertices.
So even if you have, let's say, a full cube, right? So something like this. I can just write it as this also. Here, it being in 3D in practice doesn't make the analysis in terms of graph theory any different, right?
Right.
So suppose I have this as 0, 1, 2, 3. The front face is 0, 1, 2, 3, and you have the back face as 4, 5, 6, 7. I can do this.
Okay, so that is why, sir, the Madhavan sir in the lecture did with the India's map.
That is one more thing, but well, a map is planar anyway. A map is 2D anyway. The dimension of the space in which it is does not matter. As long as you just have a set of points, a finite set of points, and a way to determine what vertex is related to what vertex, that is all that is mathematically relevant. What is V? What is E? That's all.
Okay, sir, thank you.
Now, connectedness of the graph. So connectedness is, can I go from anywhere to anywhere? This we have already discussed. I'm just writing it down.
Undirected.
It could be directed also. So
Okay, if it will form a cyclic in directed, then it will be.
so you just consider for every pair of points, can I go from, if I want to go from city A to city B, am I guaranteed that there is a set of flights which allow me to do this?
Sir, is it considering the hop, means the intermediate stop?
Yes. Not just an edge between two things. So reachability always means, does there exist a path, which is a sequence of edges, starting from one vertex, ending at another vertex. All right.
Yes, sir.
Through paths. So clearly, this graph, the friendship graph, is not connected, right? I cannot pick an arbitrary pair of vertices and say they are connected. But even the flights between cities is not, because from 2 I can't start and go there.
Yes, but it depends on vertices. If you only consider 0, 2, and 1, then it was a reachable. Yes. So if
Yeah, for now, let's just state it this way and leave it. So anywhere to anywhere, meaning for arbitrary thing, it has to work, right? For any arbitrary point, it's 2 points, it has to work. All right.
Yes, sir.
So next we will be talking about the coloring problem. Okay. There were doubts before I go to the next topic.
No, sir.
sir, does the path mean my favorable edge?
Could you repeat that?
Does the path mean the favorable edge?
What's a favorable edge?
Means the edge which I should go. Suppose you took an example.
Anywhere to
Minimum
anywhere
cost.
means
We
any
are not talking about cost over here. That would be also a further refined question. When I say, can I go? Does there exist? That's all. So we are not talking about the costs.
Okay.
All right. So next we talk about the coloring problem. So next we state a set of problems. We don't necessarily give you an algorithm or a way to solve it. This is to further motivate you to think about graphs as really effective tools to visualize certain things. So the coloring problem, the origin of it, as far as I know, is in the map coloring issue. So whenever you have, let's say, a map of something, and let's say you have different provinces, states, or whatever, and something like this. Now, if I want to color this map, right? If I want to color this map to present in a book or whatever, how would I color this? How should I color this? So I can put this as something like red. But then if I put this also as red, it would be difficult to read it. So usually what is done is these things are given different colors, right? Something else over here.
You just need 4 colors, right?
That is the
3
theorem.
will be,
That is a
yeah.
deep theorem. In this case, 4 is always the maximum that you will require. So the objective is to have no two neighbors or no two provinces or states that share a border have the same color to reduce
May I
visual
know
clutter.
what is the concept? What is the logic behind 4 colors?
The proof of the 4-color theorem?
No, I don't think so.
No. Do you want to know the proof of the 4-color theorem? Is that what you're asking?
Oh, no, not the proof, but the logic behind that.
I am not aware of the proof of it. I think it is a fairly deep result.
No, he's telling that's why.
No. I'll state the 4-color theorem. That you want the statement, is it?
Yeah.
Yeah. Okay. That we'll get to. So first, let me motivate what the problem is. The problem is I want to color this map in such a way that two provinces that share a border are not of the same color. So first I started with red, then I put blue and teal for the other things. Now I can reuse red, right? Of course, one way to do it would be use a different color for each of them. There are 1, 2, 3, 4, 5, 6, 7 provinces. You use 7 colors. If you use 7 colors, all of them will have a different color and you're done. But efficiency means you would want to do it with as few colors as possible. So wherever you can repeat, just repeat. So here we'll put red. On this, I can't put red or teal, but I can put blue.
Blue.
Right?
Means the adjacent one would be of different color, right?
Yeah, if the states share a border, then they should be of different color.
Oh.
Okay. So this is a valid coloring, right? Now,
yeah,
how do I transform this into a graph theory problem? So instead of the states, I will have vertices, right? So let's call this guy is, I don't know if this will be visible. This is 1, this is 2, this is 3, this is 4. I hope what I'm writing is 1, 2, 3, 4, 5, 6, 7. Clear?
yeah.
So let me draw the states. Let me just list the states as vertices, somewhat central to their position in the graph. So this is my 1, 2, 3, 4, 5, 6, and 7. Now, when will I draw an edge between them?
If they are
When they share a border.
If they share a border,
yes,
then I will draw an edge between them. 1 and 2, yes. 1 and 3, yes. 1 and 4, yes.
Yeah.
And that's all the neighbors of 1.
2
and 4, 2
and 4.
And first of all, would a directed graph be a right model or an undirected graph be a right model for this?
Undirected.
Undirected, because
undirected, right?
Yes.
So there's no hierarchical relationship over here. So 2 to 4, 2 to 1, both are no, 2 to 4 is not done. So let's do 2 to 4.
And 2, 1 also consider. Yeah. Okay.
2, 1 is already done.
Yeah.
So
4, 6, 3, 6.
Next, let's go
5,
to
6,
vertex
7,
3.
6.
So you
3,
have
4.
3, 1. 3, 4, 3, 6, 3, 5.
3, 4, 3, 6, and 3, 5. For 4, it will be 6. Okay, done. Now
6, 5, 7. All will be there.
6, 5,
6,
Sorry,
5, 7.
5 will be not be there.
3, 6, 7.
5 and 6 are
3,
connected.
6.
5 and
5
7 are
will be with 3 and 7.
Sir, 4 and 7 also.
4 and 7
No.
will not be because they don't share
Oh,
a border.
yeah,
right?
yeah, I am wrong. Yeah.
Okay, so this is the graph theoretic representation of the states with the with the states as vertices and the edges denoting whether or not they have an edge, a border in common. So in terms of the graph,
So,
what you want to do is, yeah, go ahead.
so if all the vertices don't touch each other, can the graph still be undirected?
Could you repeat that? If all the
If all the vertices don't touch each other, like say for 7 is like separated from all of them. Not all of them, like from 1. In no way does it touch 1. Can the graph still be undirected?
what do you mean by it is not related to 1 or not? What was the term you used?
Like
So in the
like
context of map coloring, the
no,
edges
I'm
are
not
determined
talking
whether
about
or not. Okay,
I'm not
okay,
talking about coloring. I'm talking about the
okay.
previous point.
Previous problem is
So
it?
she is asking
Yeah.
about the sharing of borders, I think.
Okay, let her speak.
No,
Can you say
if
it more
7
clearly?
is not related, if 7 is not related to any, like it's separated from all of them, all the
Okay,
other
let's say we have an
vertices.
island over here.
Yeah.
Okay, let's put another island over here. So I can give it any color that I want. That's okay.
Mm-hmm.
And let me call this guy as 8. Let's also do this. And there's this guy 8 over here. Okay,
And
so this is
let's say
also an
7.
undirected graph,
Yeah. Okay. Okay,
right?
thank you. That was
Because
my question.
yeah. So because there is no way to have a unidirectional relationship over here, right? A relationship is defined by sharing borders. So if one state shares a border with something, then the other one will share with it. It's a symmetric relationship, right?
Yeah. Thank
So
you.
that could be the idea of a bridge or something like that. Okay.
Yeah, you could put a bridge, and then if you consider that
Yeah.
sometimes
It is
there are these are considered to be maritime borders or
right.
something. There's some
Yes,
concept like that. In that case, 7 and 8 would be neighbors, and then if you also consider that. But even in that case, it would still be a bidirectional edge, right? It would be a
yes. You can go from 7 to 8. You can go from 8 to 7.
yeah.
Yeah.
So let's keep that too, just to have it. So it roughly looks
That
like
means
Africa
if
with some
the
Madagascar on
point
the coast or something. Yeah. So now, in terms of graph theory, what we want is I did tell you what it is visually, right? I want to color the graph in such a way that no two neighbors share the same color. I want just purely mathematically, I want a function called the color function, right? From vertex set to some whatever set of colors. You can assign a set of colors. I'll just put it as n. You can assign one number to each color. So
So, sir, we need to
whatever
color
let's say
differently
set of
the
colors.
independent edges, right? Independent vertices, sorry.
Yeah. So let me write this down. I want a function C from the vertex set to the set of colors such that C of V1 is not equal to C of V2 if V1, V2 belongs to E. Does this make sense?
What is E? Sharing borders relation.
It is the edge set of the graph. What is the edge set? Edge set means
Okay.
V1, V2 belongs to E, means V1, V2 is an edge
They are
in the graph.
sharing their borders.
That means they are sharing the borders.
Yeah.
So is this fine? Is the mathematical
Yes, sir.
interpretation fine?
Yeah.
So this is the objective. This is what we want. This is what we want in terms of visual interpretation and what we want robustly as a mathematical function. Both of them we have stated. And we would want to do it for any possible graph. So here we did it just by, trial and error. Is there an algorithm? So we are not going to state the answer to that question. We are just going to tell you the 4-color theorem, which says that planar graphs are 4-colorable. What are planar graphs? A planar graph is something which can be drawn on a plane without intersections. Meaning, if I take the following graph, right? Let's say I take this graph. This graph as it is may not be planar, meaning there are intersection between the edges. So this itself is not a vertex. This central thing where the intersection is happening from, there is an edge between 0 and 3, there is an edge between 1 and 2. They are intersecting. But I can just redraw this as 0, 1, 2, 3. I can do 0, 3, and then I can do 1, 2. As far as graphs are concerned, this is not any different, right? This is still the same data. As undirected graphs, these are the same. So this is a planar graph. So, and maps will always be planar graphs, right? So there won't be an intersection between two edges. And or if that is not very obvious, just assume that maps are planar graphs. So planar graphs are 4-colorable. So what is 4-colorable?
Could you explain that once? Has not got
explain
the
which
concept.
part?
Yeah, this concept.
So okay,
4-color theorem.
a graph is said to be n-colorable if it can be colored. Colored meaning I want to find a function which satisfies these properties. Okay, colored with n colors. That is as simple as that. And take for example this graph. Is this graph 8-colorable?
No.
No.
It can be, right? Like I can assign one color to each of the provinces, and if I
Yeah,
use
it
8
will
colors,
be.
I can get it.
Yeah.
So it is
Yes,
8-colorable.
Okay.
Is it of course, if it is k colorable, it is also k plus 1 colorable. If I use more colors, I can always color it anyway. But the idea is to get the minimum set of colors. So I want to do it with as few colors as possible. So what we have shown over here is that this graph is 3-colorable. It is 8-colorable. If it is 3-colorable, it is all n-colorable for n greater than or equal to 3. Doesn't matter if I take a bigger set of colors.
Yes, sir.
If I can do it with 3, I can do it with more. But the objective is to do it with as few colors as possible.
So can you explain again that, because 4-color and now you are showing me that you can do it with 3-color also. So
right. So here this theorem says that any planar graph is 4-colorable. Right? There could be graphs which are 3-colorable, like this one. Now, if I just have graphically, it's just this. This graph, how many colors can you color it with? 2 colors, right? I can put red over here, I can put blue over here, and this is 2-colorable. So the 4-color theorem doesn't say that you always do require 4 colors. It says the maximum that you will require for any graph is 4 colors. All right, so now if you ask me for an example of a planar graph which is not 3-colorable and it's exactly 4-colorable, that I don't know off the top of my head, but a Google search should give it to you easily. So is this graph 2-colorable is a good question, because we have said that 3 we can do, but can we optimize further?
Can we mix one with another?
No.
No,
The
this
set of colors
In that
cannot be
is fixed.
2-colorable.
Okay, so can anyone give me an argument why this is not 2-colorable?
So
Sir,
which one?
because
Because
if
three
we,
states share the same border
yes,
in the beginning. 1, 2, and
yes,
4.
Yeah, so 1, 2, and 4. The thing is, 1 and 2 need to be given 2 different colors,
Yes, otherwise
right?
it merges and it looks like just one.
And then 4 shares borders with both 1 and 2. So it has to avoid the colors of both 1 as well as 2, which themselves share a border, right?
Yes, sir.
So this has to be at minimum 3 color. So you need a minimum of 3 colors, and using 3 colors, we have actually colored it. So this is actually 3-color. This is an example of a graph which is 3-colorable. So here is an exercise, or you can quickly resolve it also if you have understood it. So if there is a 3-cycle, do you know what a 3-cycle is? Something like this. Okay, if there is a 3-cycle in a graph, somewhere in the graph, this is not the whole graph, there is some component where you have this 3-cycle in a graph, then it requires at least 3 colors. Is this obvious? I use OR sometimes, OUR sometimes for color, but yeah, ignore that. Is this exercise doable? Just on the spot?
yes,
Why so?
sir, because we get 3 adjacent edges.
Yeah,
So
so
for
if I
that we
pick
need,
any 2 of my
yes,
choice, they need 2 different colors. And the third edge, the third vertex is also adjacent to both of them. So it has to have a different color. So as soon as you have a 3-cycle, you need at least 3 colors. But what about a 4-cycle? What if you have
we
something
use
like
3.
this?
2 colors.
3 is the base.
2 is sufficient, right? Like just
Two is
for
fine,
this part.
yes. Opposites.
So I can just do red, blue, red, blue.
Yes, 2 is sufficient.
2 is sufficient, but yeah, you should see what is happening in the rest of the graph. So this is not like n cycle is n-colorable, of course.
What if the blue and blue touches each other?
Yeah, so then you have to look at this completely connected graph, right? So
Okay.
so the
Yes.
thing is, if you have a finite set of vertices where everything is connected to everything, that is called a complete graph. Okay, where your edge set is not V cross, it's not merely a subset, it is exactly this minus that diagonal meaning a comma a type elements. Every vertex is connected to every other vertex. So take for example 4, this is connected to this, this is connected to this, this is connected to this will be connected to this, and this will also be connected to this. This is what is called K4. So in this case, you need at least 4 colors, right? Why is that?
Because everything touches each other.
Yeah,
Yeah,
because
so
it's
here,
same
if I
object.
have color 1, color 2, when I look at any other vertex, it is connected to both of them. So I need a new color. So I look at any other vertex, it is connected to everything. So I need a new color, right?
Yeah.
So this is also one exercise. This is exercise 1, let's say exercise 2. Kn is n colorable. Well, Kn requires n colors. It's not just that it's n colorable. Kn meaning complete graph. If you don't know what this is, just look at complete graph. Requires n colors. Not very important, but just good to know. And what is this? This is just K3 actually, right? This is a graph with 3 vertices where every vertex is connected to every other vertex. But if Kn requires n colors, then K5 would require 5 colors, right? But I've said that every graph is 4 colorable. At max, you will require 4. So what is the conclusion? Is there any contradiction that's happening?
So, sir, at max, the minimum number of colors required is 4.
Minimum can be 3 also, right? We just
Planar graphs can be that, but so Kn, I'm saying it requires n colors, meaning it is only n colorable or more. Well, it's so K5, if you take K5 for example, if you take 5 vertices and then connect everything with everything, do this, 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 and this, and this. So this requires 5 colors. This is not 4 colorable.
Right. So a complete graph is a graph where all the vertices are connected to each other.
It's a graph with n vertices where each vertex is connected to every other vertex.
Every other vertex, okay.
All right. So that's Kn.
But
now K5 requires 5 colors, right?
So
Yeah.
won't n be the maximum number of colors possible?
That's also true for a vertex for a graph with n vertices. N is the maximum number of colors that you require. You can put n plus 1 and not use one color. That is always there. But n is the absolute maximum you require anyway. But what it says is that for a complete graph, you do require all of them.
Okay.
So my question now is, I said every graph is 4 colorable. I didn't say every graph, but yeah, that's the point. But K5 is not 4 colorable. By this diagram, K5 is not 4 colorable.
Basically,
so
these are contradiction, yeah.
It's not a contradiction because we have not talked about any graph. We have talked about planar graphs. So K5 is not planar.
Okay.
So that's the thing, right?
So this could be a true or false kind of a theoretical question.
Sir, so it can be only true if the graph is planar, right?
Yeah. So you can try to draw a planar version of it, a version of it. So K4 was this, right? I can draw a planar version of it. I can draw this. This is planar. There is no intersection between the edges. On a plane, you can draw it without any edges crossing each other.
So planar
but can you do
means-
the same to this?
So planar means no intersection of edges, right?
Yes. So there might be some representations of the graph where there are intersections, but I can always redraw them in such a way that the edges don't intersect. So planar means can be drawn without edges crossing each other. All right. So you could try to redraw K5 as a planar graph. You will see that you will fail, of course. Otherwise, our 4-color theorem would be false. So this is one thing. So coloring maps doesn't seem like a very important thing to do, is one way to put it. So another way, another place where the coloring problem occurs is classroom scheduling, right? So if I want to have a few courses run, and the thing is I want to use as few classrooms as possible. So suppose I have courses which are titled C1 to C6. Let's say I have 6 courses, and the schedules for them are out, right? So this runs from 9 to 10, the other one runs from 9 to 11, whatever. So assume that that data is given. 6 courses are there and their time slots are fixed. Just one moment. So I will draw a graph now with this C1, C2, C3, C4, C5, C6 as the vertices. Now I will draw an edge between 2 courses if their time slots have clashes. Suppose this is from 9 to 10. So C1 is from 9 to 10. C2 is from, or let's keep 2 hour slots so that we can have clashes properly. So this one is from 10 to 11. So C3 is from, let's say 15 to 10 to 12 we need, right? Everything is a 2 hour class. Let's just assume for some. C4 is from, let's say 13 to 15. This is from, let's say 11 to 13, and some 14 to 16, something like that, right? Now, can I have class 1 and class 2 in the same classroom? Course 1 and course 2 in the same classroom?
No.
No, because their time slots have a clash. So whenever there is a clash between the time slots, I will draw an edge between them, right? So the edge, the relationship is defined as, once again, this is an undirected graph, because if there is a clash between 2 courses, that goes both ways. So using the data of the time slots that is given, I can draw the edges now. From C1, 9 to 11 clashes with what? 10 to 12, yes. Not 15 to 17, not with anything else, right? From C1 or from C1, there is only clash with C2. But what about C2? C2 has clash with C1 as well as C5. So we'll draw that edge. Next, C3. What about C3? It has clashes with C6 only?
Okay.
But it is C4 also.
No, 13 to 15, 15 to 17. So that is not a clash, right? They can vacate the class and this will start instantly. That's fine. Okay, so assume that 13 to 15, 15 to 17 is not a clash, right? From C4, what are the clashes that are possible? There's C6.
C6, yeah.
That's it. C4 is only C6.
For C5, it will be C2.
C5, C2 is already done.
Yeah.
Is there anything
C5
else?
to C1. C5 to C1.
C5 to C1 also there's no clash, right? 9 to 11,
But
11
it
to 13,
also
that is
gives
joint.
9 to 11. Yes. Yes.
Okay, and the last one is C6. For C6, have I written down all the clashes?
Sir, it can be C3. Yes. C6 to
C6 to
C3.
C3 is already done, right? Taken care of.
C4
Okay,
also
so,
done, yeah.
Yeah. So in this case, it's a disconnected graph. So individually, the components you can, let's try to get some clash between them so that I will make it a connected graph also. Okay, let's maybe leave it over here. Now, okay, I just want to tell you why coloring makes sense in this context. So let's go about it. Now, if I want to determine the maximum number of classrooms that I require to run each course, how would I do it? So if I assign, let's say, classroom 1, so I'll just call it room 1 to C1, I cannot assign room 1 to C2, right? There will be a clash. So
Yeah.
I have to give this guy another room. But to C5, I can give the same room 1. That is okay. Because C5 runs later.
Yeah, 11 to 13.
Yeah, so this I can give room 1 again. Similarly, over here,
Also C3
C3 also I can give room 1.
and similar to C6 also.
Now I'm
C6
getting
I
the
cannot
point.
give room 1, right?
I have to
I
give
have to
room
Can
give
2
give
the
because
room
edge.
1
it
to
is connected.
C4.
I can give room 2, room 1. This is okay. But what is this assigning of rooms that we have done? It is like assigning a color. So it's color is just a psychological thing. So you can just call it a room. You can just call it whatever. You can just put some indicator there. And what we have avoided is giving the same color or the same room to adjacent things. So do you see why this is a coloring problem?
Yes, sir. Now it is clear.
So what we are looking for is assignment of a function from some finite set. We may call it colors or we may call it rooms. But what we are avoiding is adjacent vertices. Adjacent vertices meaning there is an edge between them, not a path. In this case, it's an edge. If there is an edge between two vertices, then the color or room that you assign should not be the same. In the case of maps, this is the same thing we did, but we called it colors, right? So we had, if there is an edge between two vertices, then there should not be the same color given to them, right? So it is exactly the same thing that's happening, but here we are calling it rooms. So this graph is too colorable. So instead of calling it rooms, if I said determine the number of colors required, would you not say blue, red, blue, blue, red, blue? We would say the same thing, right? It's just a matter of language. And this is why classroom scheduling also falls under a matching problem. Is that clear?
Yeah.
Now, how to actually determine the minimum number of colors is not something that we are going to see. Most graphs that you're given will be small enough for you to play around with and get the answer for, even if it is asked. The algorithms itself, we will not be dealing with in the course. We are just demonstrating how we can translate, how we can, with using a good analogy between relationships, how we can convert problems to to a graph theory problem, and then use whatever knowledge we have of that to get to where we want.
Sir, I
Okay.
remember a problem. I think it might be in my previous book. Previous textbook. There was a way in which a mathematician built a bridge like this only.
Yeah, that is that Euler's problem or something, I think. But let's not go off track
Yes,
because we are already out of time. So let me at least cover what I have prepared.
yes, only.
For the
Yes.
BFS and DFS will be taken up in the next session itself, but at least the remaining we should finish. So let me quickly go through the rest of the stuff. So next thing is a vertex cover. This fall in the category of what one of you was saying earlier about putting some vertices as redundant or something like that. The graph theory problem is if I'm given a graph is vertices, edges. So let's just do some graph between these vertices. That's sufficient, I think. Yeah. Let's call this 0, 1, 2, 3, 4. I want to choose a subset of vertices which covers all edges. Now, what does covers all edges mean? Suppose I choose vertex 0. Then this edge is taken care of. Are all edges taken care of? No.
No,
But
no.
one of the edges is taken care of. Now, let's say I pick 3.
Okay,
Look
so
at
we
all
take
the edges connected to
we
this.
we took 2.
So yeah, let's go step by step. Once I took 0, one of the edge 0, 2 is gone. If I choose the vertex 3, there are 2 edges which are connected via 3, which is 3, 2 and 3, 4. It is an undirected graph, so I'm not going to say in which direction. So, but still not all edges are taken care of. So I will take the vertex 4 now, which means 4, 3 is already in my, that edge has been accounted for. The other edges that have not been accounted for is this, right? So a vertex cover. A vertex cover for this graph is 0, 3, 4. The order doesn't matter. So what is a vertex cover? A vertex cover is a subset of vertices such that if you look at all the edges which are adjacent to these vertices, meaning the edges which are a part of, for which these vertices are a part, then you will exhaust all the entire edge set. So this is a vertex cover. Of course, the vertex cover is not unique, right? So if instead of this, I considered, instead of 0, 3, and 4, what if I started with, yeah?
It can be 2 and 4 also, right?
Yeah, that's what we are going to do now.
Oh.
Let me take 2. Here I've taken care of this, and this. If I look at all the edges for which 2 is a part of, I can remove those 3 edges. What are the edges that remain? 1, 4 and 4, 3. So if I take 4, so a vertex cover
2 and 4.
for this graph, this is also a vertex cover. So this doesn't mean this is not a vertex cover. It's the same graph, but ideally for real world applications, we would want the minimum number of vertices which cover all possible
Points, yeah.
points. Yeah. So
So
let's
are
say,
we finding the edge with
go ahead,
cover
anyone,
the
one of us.
like this?
Other doubts?
Yes, sir.
Please. Yeah.
Not a doubt, but just an observation. So this becomes a good application for, let's say, the delivery riders who travel around the city and they have to cover,
Yeah,
let's
maybe
say,
you can put the delivery guys pickup points, the where they load
Yes.
the groceries in these places, so that
Right.
these are connected to everything else, right? It
Yes,
covers
to,
all the streets. So think
yeah.
of this as a map of edges. Or if you want to put let's say a traffic police check, so
Right.
any road goes through one of these vertices, right? So that's the
Right.
point.
Yes, so
So
we need to have lesser number of riders to cover maximum number of streets.
yeah, so I can, if I put a traffic police over here and traffic police over here,
Yeah,
then any
they
guy
can
who's
check.
taking any road within this within the roads
Yeah.
that this graph covers, you can
Right.
have a check whether he's wearing a helmet or whatever.
Or,
Yeah. Well, you can think of
or,
applications.
or similar to maybe a school which has the ones who take care of uniforms and stuff like that. Anything like that.
Even that is true. So what Professor Madhavan uses is CCTV cameras. If I put a CCTV
Yes.
camera and one over here, I have basically coverage of the whole thing, assuming that the CCTV camera has it sees all the streets and all that, all those practical things you for now just discount. And you can easily come up with applications for this sort of problem. So this is called the vertex cover problem, finding the minimum number of vertices which cover all edges. Right?
Yes, sir. Even in problem in football, where a player takes care of a certain part of the ground or stuff like that.
Yeah, you could come up with creative examples. I don't immediately get what you're saying, but let's not spend more time on it. All right. So
Sure, sure.
we have some other graph theory problems that we
Yes, sir. Thank you.
have to at least discuss before, let's say, 10-15. Now, next thing is the independent set problem, right? So here we also want a subset of vertices, but here the thing is different. The objective is different. So let's maybe take the same graph or have it over here. So here we say that a subset of vertices is independent if, okay, I've already written, right? Yeah, subset of vertices such that no two vertices are connected by an edge. So if I consider the collection, let's say 0 to 4, this is not an independent set because there is an edge from 0 to 2, there's an edge from 2 to 4. So suppose I start with 0. I cannot put 2 in there.
But I can put 3.
I can put 3.
Then I can put 1.
Then I can put 1. This is an independent set. Once again, the independent sets are not unique, is an independent set. Right? So if I start with 2, what happens?
I can use only 1.
Only 1 is the continuation possible, is an independent set. So
Excuse me,
in the
sir.
context of independent sets, yeah.
In the independent set of 0, 3, and 1, why 4 is not included?
Could you repeat? I couldn't hear you clearly.
In the upper set, 0, 3, and 1, why 4 is not
Yeah.
included?
So as soon as I put 3, you can't put 4, right? You cannot have 2 vertices in the independent set which are connected by an edge. The requirement is that if you pick any 2 edges in your set, subset of vertices, then that should not be connected with anything else. So the example to visualize why such a thing would be important or interesting is I am just going to restate what Professor Madhavan said. So it's like you're organizing cultural program and there are a set number of items and each person knows a certain set of performances. Now the vertices on this graph, they represent the people and there is an edge between them. Wait, the vertices are not the people. The vertices are the performances. Suppose there's a music school in which people know 5 songs. Let's say we put the songs as the vertices, and we put an edge between 2 songs if they both share a performer. Right? When we are organizing a program, we want to give everyone a chance, along with the fact that one person doesn't come multiple times. So when I choose song number 0, let's say, then I won't choose song number 2 because there is a overlap in the performers there. So then I choose 3, then I choose 1. So here we want to maximize the number of performances while also keeping no clashes between performances. So this is one application of that. All right, so I'll quickly go on to the matching and then adjacency matrix. Probably topological sort also I'll have to cover in the next session itself. Next session will go slightly faster.
Sir, in the previous graph, there are more sets, right, which are independent?
Yes, you can, of course, we have not even considered 4 over here. Let's say you start with 4. How can you continue this?
4, 0.
2 and 0. 2 and 0.
Only this thing is one choice.
Oh, yeah.
Even
Sorry,
if I start with 0, if I do 4, then it will be, yeah. So there are many. So here we would want to do, depending on what you want to do, you would want to minimize or maximize it.
So even 3, 1 will be another subset of 0, 3, 1, right?
3, 1 is also an independent set, but yeah, it doesn't cover it. Yeah.
Oh, but it
So
has
here
to. Okay. Yeah.
It does have the property that it is not these are not connected by an edge. So you can take any V1, V2 which are not connected by an edge, and that is an independent set.
So that is valid, right?
Right.
V1 also is a valid.
That is valid, but mostly it is maximizing the number of vertices. What is what is important over here.
Okay.
So this would be the more ideal thing.
Right. Okay. Got it.
Sir,
So how many performances can you put out? Like among all the performances known by your music school or whatever, what is the maximum number you can show while also ensuring that the same person doesn't do it twice, right? Doesn't appear twice. So that is one way to think about it. Okay, yeah, there was another doubt.
yeah, sir, are we writing this set like first we wrote 0, so the 3 and 1 we wrote these elements with respect to 0 or like overall independently?
So if I did not tell you the procedure of how I got this and I just said 0, 1, 3 is an independent set, there is a way to verify it, right? You check whether 0, 3 there is an edge, 3, 1 there is an edge, 0, 1 there is an edge. If there is no edge, then it's an independent set. So it is not with respect to 0, but of course it does depend on each of the elements somewhat equally. Whether the set is independent or not, you just have to check this condition. Is this condition satisfied? Then it's an independent set.
Yeah, okay.
All right. Now for matching, we have the other problem, as in here we don't talk about subset of vertices, but we talk about a subset of edges. Instead of saying the vertices are not connected by an edge, we say the edges that we choose should not be incident at the same vertex. Right there, here we say it's mutually disjoint.
Can you just
Sorry?
Sir, what did you say now? Can you just explain it?
Yeah, so here we said in the independent set problem, we wanted to cover vertices in such a way that there are no edges between them. Now, what is the corresponding problem for edges? So if I have 2 edges, wait, what happened? Okay, right. So if let's say 2 edges, these are not independent, right? So they are incident at this point.
Okay.
Let me call these guys E1 edge. These are edge names. They are not weights or anything that I was talking about earlier. I'm just giving the name to this edge instead of writing it as 0, 2, 2, 3, so on. I just call it E1, E2, E3, E4, E5. Now let me construct a set of edges which were disjoint. So they are not disjoint, if there is a common vertex. So if I select E1, can I select E2?
No, they share a common vertex.
Yeah, so
But you can
E3.
select E4 or E5.
So I can select E4. So I'll do this, but then I'll have to close it, right? Because then E5 also I cannot select. So it's just this and this.
So why can we not select E5?
Because then it would be incident at this, right? It's not mutually disjoint.
But it
Yeah,
is
okay.
not connected with E1.
So I can
No,
do even
we are
E5. This is okay. All right.
Okay,
So
you
both
mean
of
all
these
three
are,
not okay.
yeah, they should be mutually disjoint. Meaning any pair should be disjoint. Are
Yes, all
matchings.
three must be disjoint.
Right. So these both are the two of these are a matching. But in this case, there is no perfect matching, right? So the model for this sort of problem is you want to assign a group project, which you can do. So depending on friendship or capability or whatever, you have listed the members in your classroom and you have put an edge between them if they can do a project together. So for example, 0 and 2 can do a project together. 2 and 3 can do a project together. So let me just put this one more 5 over here and put this edge E6 over here just to make it better. So in this case, these are matchings, but I can also add E6 over here. Now you want to break the class in such a way that projects are assigned. So one guy can't do two projects, right? So as soon as I select E1, I am saying that 0 and 2 are going to do the project together. Now 2 cannot do a project with 3 or 4. The other possible pairings for 2, they are eliminated. Is that correct?
Yeah.
So as soon as I say that, okay, 0, go and do the project with person 2, the 2 is taken away. The 2 cannot do a project with 3 or 4 anymore. But 3 and 4, they can do a project by themselves. So that is okay. But as soon as 4 takes 3 as his partner, 1 cannot do a project with 4. But in this case, 1 can do a project with 5. This is what is called a perfect matching, which is a matching in such a way that all vertices are accounted for. Instead, if I let me just call this is a matching. And instead, if I take the following thing, so if I start out with E1, I say, okay, 0 and 2 go and do a project together. And then from among the remaining, I say, I pick E5, meaning 1 and 4 go do a project together. Can 3 and 5 do a project?
Yes.
3 and 5 are not compatible partners. So they cannot do a project
they
together because
do not have an edge. That's why.
Yeah, E1 and E5 can.
so when E1 and E5 are done, 0, 2 and 1, 4 are done. Right now, what is remaining is only 3 and 5, but they cannot do a project together. So this E1, E5 is a matching, but it is not a perfect matching because some vertices are left out. Remember that for a matching, all that is required is that you have chosen a subset of edges which are mutually disjoint. E1 and E5 are disjoint. That is a matching. That is one way to assign projects. But then 3 and 5 won't be able to do. So this is not a perfect matching. So
Right. So,
instead, if you say,
so the reason
let's say, it's just
the
one
reason why-
minute. Let me complete this statement. So if I say the projects can be done in groups of 2 or they can be done solo, then 0, 2, 1, 4 and then 3 and 5 do it by themselves. That is okay. That is one way to assign projects, but it is not a perfect matching because not all vertices are taken care of in the matching itself. Okay. So yeah, what was your doubt? Is a
Yes.
matching, but not a perfect match. All right. So this is the matching problem. So we have, using real life scenarios, we have seen how graph theory, you can cleverly modify it to a graph theory problem and then ask it purely in terms of does there exist a subset of V cross V with certain properties, or does there exist a subset of V with certain properties? So it clearly becomes just a maths problem, but the underlying idea is something which is
So
motivated
excuse
by
me.
The first
real
one is
Excuse
the
me, sir.
perfect matching, right, sir?
Hello. Excuse me, sir.
Yes, one at a time,
Sir,
please. Yeah.
sir, can you show that one independent sets above to that? So what was that?
This
I
one?
want to see. Yeah, yeah. It was dependent, this one.
No, this is called vertex cover problem. So here you are choosing a set of vertices which covers all edges, is all that is. So these are this is not, these problems are not related to each other as is.
No, like I thought this second one was independent. So I thought the first one above to that will be maybe
Yeah,
dependent.
yeah. Don't connect these two things which are
Okay.
themselves independent.
Okay. Okay. Thank you, sir.
Yeah, the
Excuse
independent
me,
is
sir.
independent from the vertex cover problem. Yeah.
Independent set is likely opposite of matching, right?
It's not opposite. What do you mean by opposite? So it's
Like
something like a dual. Dual means when you can. I don't want to go into dual of a graph, but
Okay,
here we are
clone,
doing
clone,
it
clone.
for vertices. Play the role of edges, and edges play the role of vertices. If you can think of it that way, then
yeah, that
So,
one.
yeah.
excuse me, sir.
It will be a clone of them.
All right. Yeah. What's the doubt?
Yeah. So the first version is the perfect matching one, right?
Yes, this is a perfect match.
Oh, wow.
All right. So then we'll stop with the adjacency matrix, and I'll somewhat give a very quick overview, and I'll pick it up from there and then go to topological sort and BFS, DFS quickly in the what is supposed to be a doubt session, but we'll do this and then take doubts. All right. So on Tuesday. So all of this is nice to see for a human, whatever, and understand. But how do you work with it? How do you how do you code it into a machine readable thing, or even for you to work with? One way to do it is a graph is represented by a unique matrix, and a matrix which has entries 0, only from 0, 1. This corresponds to a graph. So how do we do it? Let's take the same example since we have it already, and maybe even put another vertex 5. So here there is nothing special about these guys. This is a graph, right? Now I can draw a 6x6 matrix. A matrix. Have you been introduced to matrices in any form anywhere?
Yes, in CT, sir.
Okay, then
Thank you.
that's good. I'll not go into what the order of the matrix is and all that. So okay, there might be some people who have not done CT who are coming to Math 1 for the first time. So I'll just say it's just a table of values. It is, when I write m cross n, it is m rows, n columns. All right, 6 rows, 6 columns in this case. So whenever the number of rows and columns are the same, we call it a square matrix. This is a square matrix with each row corresponding to your vertices and column also corresponding to the vertices 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. Now, all the entries in this matrix are 0 or 1. It is 0 if there is no edge between the two vertices, and it is 1 if there is an edge. It's as simple as that. So diagonal entries are all 0. Why? Because there is no edge between a vertex and itself, right? And if it is an undirected graph, this is a symmetric matrix. Why is that? So take, for example, 0, 2. there is an edge between 0, 2. So the entry over here, 0, 2 is 1. But that means that there is an edge between 2, 0 also. So this is also 1. Look at 0, 0, the vertex 0 and the vertex 1. Is there an edge between them?
No.
No. So automatically this becomes 0 as well as this becomes 0. So you write the rows and columns of the matrix indexed by the vertex set, and you look at the corresponding entry. So here, if you look at the ijth entry, it corresponds to row I, column J, right? Which means it is vertex I to vertex J, whether there is a edge or not. This is an edge, not a path. Remember, this is not connectivity or anything. This also comes from the adjacency matrix later, but for now it is just an edge. It detects the existence of an edge between vertex I to vertex J, the ijth entry. So you can complete the rest of the matrix. So you will get a 0, 1 matrix. So from the graph to the matrix, you know how to do. Now, if I give you a symmetric matrix, let's say 0, 0, 0, 0, and 1, 1, 0, 1, 0, 0, and the same thing over here, 1, 1, 0, 0, 1, 0. Right? This is a symmetric matrix. Can you draw the graph corresponding to this? What is the number of vertices on this graph?
4.
4. So let me just draw 4 vertices in whatever fashion. I'll call them 0, 1, 2, 3. So this is the standard convention.
ABCD. We can use ABCD. Okay.
We can use ABCD, but the course uses this 0, 1, 2, 3
Okay.
throughout. Yeah. So we'll stay consistent with that. Is there a vertex from 0 to 1? So this is corresponding to 0, 1, 2, 3 vertices. This is 0, 1, 2, 3 vertices. Is there a edge between 0 and 1? Yes.
Yeah.
Right. Because the 0, 1, 0,
And
1 entry
also
is
from 0 to 2.
Also from 0 to 2.
Yeah. And 1 to
0
0
to 3 there is not, right?
Yeah. 1 to 3.
So actually I just need to look at this upper triangle because it's a symmetric matrix, right? So the same information will be given there. But anyway, if you want to go through each and every entry, you can do that as well. You will see that many of them will be redundant. 1, 0 is done. 1, 3,
yeah,
that we have not
1,
written
3,
down.
yeah. It will be, then it will be 2, 0. Okay, done. And 3, yeah, okay.
So this is the graph, right? So adjacency lists I'll do in the next session. Let's just do adjacency matrix of directed graph. So this was for undirected graph. Where it just detects whether or not there is an edge between the two vertices. So is it clear how to go from graph to matrix and matrix to graph both ways?
Yeah.
Now for a directed graph, things are slightly different. Let's say I have the following directed graph. Let's say something like this. I have this direction. Here I have both directions, 0, 1, 2, 3, 4. Here I have this direction, and let's say here I have this direction. Now the adjacency matrix, the size will be the same, and it will be indexed by
0, 1, 2, 3.
0, 1, 2, 3, 4, 0, 1, 2, 3, 4, the entries. And the diagonal entries will again be 0 because there is no vertex.
0 to 1, 1.
Now the thing is, we will put a 1 as an entry of this matrix if there is a vertex starting from 0 to 1. So I'm looking for this entry. So how do I calculate what this entry is? Does there exist an edge starting from vertex 0 and ending at vertex 1? That is true. But as opposed to the undirected graph case, look at this entry 1, 0. Is there a edge starting from 1 ending at 0?
No, in that not.
No.
So this is a 0 over here. And if I look at the other vertices, this will all be 0. Why is that?
because it is directed. So it's, yeah.
So if I want to look at this row corresponding to vertex 0, I have to look at all outgoing edges from 0, right? All of these
Yeah.
are indicators of whether or not there is an edge starting from 0 to the corresponding vertex. So now if
Yeah.
I look at vertex 1 or the row 1, how many outgoing edges are there?
There are 1, 2, 3.
Okay.
1, 2,
From
3.
1, how many outgoing are there? 1, 2, 3 only.
So one,
So
only
Yeah.
one.
it is just this, and the rest are all 0,
0.
right? From
From
2, how
2,
many
it
outgoing
will
edges are
be
there?
1 and 4.
So 1 and 4, the rest are 0.
Otherwise 0. Yeah.
From 3,
It will be only 1.
only for 1 there is, and then there's nothing else. For 4, everything is 0, right?
No, so, in the place of 1, write 1.
Okay, yeah,
In
sorry.
the, yeah.
So clearly this is not a symmetric matrix, meaning it is not symmetric across the diagonal.
Yeah.
And if I add all the row values, what is that number that I get?
It
It
will
is
be,
the number of outgoing edges. Okay. So if I look at
yeah.
this 2 and look at all the entries and I add all the entries over here, 0 plus 1 plus 0 plus 0 plus 1, which is basically what is the number of ones that appear, is exactly equal to the number
5.
of outgoing edges.
Yeah, it will be
What
5.
What is 5? Where is 5? Number of ones is 2, right? There's just 1 and 2. And that is exactly the number of outgoing edges.
Okay.
So I
Right,
think
so
he total all the ones possible. That will be 5.
okay. That would be the number of directed edges. Yeah,
Yes.
that would be the total number of directed edges.
We
So,
can
which means that this is 2. There are 2 edges over here, which are written on top of each other. Right. So what is the number of ones in a column correspond to?
The incoming.
Yeah, the number of incoming edges, right?
Yeah.
So even if you are given just the adjacency matrix, there is a lot of data that you can derive from it, right? So of course, you can redraw the graph itself. So I am not going to do it now because we have already run out of time. But just like we did it for undirected graphs, from graph to matrix, from matrix to graph, we have 2 methods. Similarly, if this was the thing given, can you not draw the graph?
Yeah.
You can draw it, right? With the
Yeah.
understanding that if the ijth entry is 1, then there is a edge from vertex I to vertex j.
Yeah.
All right. So the mathematical representation of a graph, in addition to explicitly listing out the vertex E, edge set E, the compact way of doing one of the ways of doing it is using this matrix. You will see that this is powerful to compute the number of paths also later on in week 11. But this matrix contains the entire information about the graph. Now, let's just, for the sake of it, talk about the reachability problem. Is 1 reachable from 4? If you want to, suppose this diagram is not given to you. So since the diagram is given to you, you know that 1 is not reachable from 4, right?
Yeah, it will be 0 then. We can conclude, yeah.
Yeah, so if not, how will I go about doing it? I will start with 4. Look at all these things.
Yeah.
What are all these edges? These are the edges, the ones, the edges, the vertices corresponding to wherever there is a 1 is its immediate neighbors, right? These are the edges which it is connected to. But 4 is not connected to any edge, as in there is no edge coming out of 4. So if you cannot reach any vertex from 4, let us ask if we can reach 2 from 0. From the diagram, what is the answer?
No, yeah, it will be
Can I reach 2 from 0?
No, sir.
No, sir.
No, right?
You
So
cannot.
now let us look
No.
at the adjacency matrix. The adjacency matrix, if I start from 0, the vertices
Get
that
one.
I can reach are just this one. So that is vertex 1, right? So then I look at all the vertices which start from 1. So that is only this guy.
And no 2.
So I can go to 3. Now, if I start with 3, the only thing I can go to is 1,
1.
which I have already visited. So I can
Yeah.
just go back and forth with 3 and 1, 3 and 1, 3 and 1. Right. So 2 is not reachable. So even without this information, you could have concluded this just by tracking the ones on the graph. Ones on the matrix. Is that clear? It might not be an efficient way, but it is a way, right?
Yes, sir. Yes.
It's not an algorithm, but it is one way to do it. You start at the vertex that you're interested in as the source, look at all the possible ones, mark them, and go to those rows and look at all the ones there, mark them. And if you're visiting a vertex that has already been visited, you discard that because you're running in cycles then. Then you do this, whatever inefficient way there is, and see if you can reach whatever vertex you intend to.
So for every
So
time in the directed graph, there is nothing any symmetry.
for the directed graph, there need not be symmetry. Yeah. There
Yeah.
will be, if it is, if not all vertices are bidirectional, and we can actually, in that case, assume it's an undirected graph, except for that case, this will not be a symmetric matrix.
Okay. Yeah.
Right. So hopefully you understood how to construct the matrix, and you can see that it carries the whole information, albeit not so visually clearly. It is still powerful. Right. So if you can now see that you can write the algorithms saying that start with this vertex, look at all its ones, and then go to those vertices. So you can craft an algorithm for the reachability problem, and that is what we are going to do. So in the doubt session, that's what we'll do first: the breadth first search and the depth first search, and then we will also look at topological sorting. And we'll stop now. It's already half an hour past the time, and yeah, I'm sorry for taking too long. Doubts also we'll take in the next session if there is nothing immediate. Is that okay?
Okay, sir. Thank you, sir.
The topic was really interesting, sir. So yeah, extra
Yes, sir.
time is
Thank you
worth
so
it.
much, sir. Yes.
All right.
Okay, sir.
Thanks for
Thank
your
you,
time.
sir.
Good night.
Thank you, sir. Good night, sir.
Good night, sir.
Good night, sir.